So I want you to imagine a toddler just standing in a dirt patch right outside the perimeter fence of this massive, high-security, billion-dollar quantum computing lab.
Right.
And this toddler is clutching one of those cheap plastic walkie-talkies, just mashing the transmit button and shouting, hello, is anyone there? Over and over again.
Blasting it into the void.
Exactly. And all they hear back is just the hiss of static. So after a few hours of this, the toddler looks at the walkie-talkie, looks at this giant, silent concrete building, and, well, logically concludes that the building must be completely empty.
Because if anyone was inside, they would have answered the radio.
Right. I mean, it makes perfect sense to the toddler. And that right there is basically humanity in the year 2026.
Yeah, it is a devastatingly accurate picture of where we stand right now.
We really do hold on to this incredibly grand, romanticized vision of our search for extraterrestrial intelligence. I mean, we build these massive radio dishes out in the desert.
The golden records on the Voyager probes.
Yeah, exactly. We launch gold-plated records out past the heliosphere. We beam these targeted laser pulses at distant star clusters. We feel like we're these ultimate cosmic explorers bravely reaching out into the dark.
We think we're being so loud and so visible.
We do. But the stack of sources we are diving into today, it really demands that we completely flip that entire narrative on its head.
Yeah, we have a fascinating collection today. We're looking at recent astrophysics papers, SETI reports, statistical models, and some really advanced quantum communication theories.
And the mission of this deep dive is to explore a central thesis that is, honestly, kind of terrifying.
It really is, because the thesis isn't that the universe is just this empty, sterile void. The idea here is that the deafening silence of the cosmos is actually an engineered state.
Meaning they're out there.
They are out there, but these highly advanced civilizations are actively, deliberately hiding from our specific level of technological development.
Which is just a huge paradigm shift. But to understand the mechanics of that, the actual physics of how you hide an entire galactic civilization.
And why you would even want to.
Right, the chilling reasons why. Before we get into all that, we first have to dismantle this massive psychological roadblock, this myth that has completely skewed human astrophysics for, over 75 years now?
Yeah, easily. We're talking about the famous Fermi Paradox.
Right. The idea that if the universe is so vast and so old, someone should have visited us by now. And because they haven't, they must not exist.
Which is funny, because the grand irony of the Fermi Paradox is that Enrico Fermi never actually proposed it.
Wait, really? The guy it's named after didn't even come up with it.
No, he didn't. If you dig into the historical record, and we have a really thorough forensic breakdown of this, published by Robert H. Gray in the journal Astrobiology, you find that Fermi never published a single paper on this topic.
So where did it come from?
The entire concept stems from a casual lunch conversation. This was at Los Alamos National Laboratory back in the summer of 1950.
Okay, so let's put ourselves at that lunch table. Who was actually there, and, what were they even talking about?
So you had Fermi sitting down with Emil Konopinski, Edward Teller, and Herbert York, basically some of the absolute greatest minds in physics at the time.
Just a casual lunch with the architects of the atomic age?
Exactly. And the conversation was actually sparked by this whimsical cartoon in the New Yorker magazine. It was blaming a recent rash of missing municipal trash cans on flying saucers.
Oh, because of the whole UFO craze going on back then?
Right. The Roswell era,
Yeah.
They were joking about the UFO craze. And Fermi, who was famous for his ability to do these incredibly rapid order of magnitude estimations entirely in his head.
What we call Fermi problems now, right?
Yes, exactly. So he just goes silent for a moment, does some mental math, and suddenly asks the table, where is everybody?
But according to Gray's research, he wasn't actually talking about the existence of alien life, was he?
Not at all. And York and Teller both went on the record later in life to clarify this. Fermi was calculating the sheer energy requirements and the physical logistics of crossing interstellar distances.
So it was a physics problem for him, not a philosophical one.
Right. He was looking at the speed of light limit, the massive distances between stars, and the astronomical amount of energy you'd need to accelerate a physical mass to even a fraction of that speed.
And what was his conclusion?
His conclusion was essentially, space is too vast and the energy cost is just too high, so physical travel between stars is probably unfeasible.
Oh, wow. So he was just saying the commute is too long.
Exactly. He never once suggested that intelligent life doesn't exist elsewhere. He was simply arguing against the likelihood of physical visitation.
Okay, so if Fermi was just doing some back-of-the-napkin math about the fuel costs of starships, where did this paralyzing philosophy of absence of evidence is evidence of absence actually come from?
Well, it took a while.
Yeah, how did it get slapped with his name?
That didn't happen until a quarter of a century later. In 1975, a scientist named Michael Hart published a paper making a very, very different argument.
What did Hart claim?
Hart claimed that any sufficiently advanced intelligent life would inevitably expand, colonize its neighboring stars, and eventually sweep across the entire galaxy.
Like a galactic empire.
Right. And he argued that because we don't see them walking around on Earth right now, they absolutely must not exist anywhere in the Milky Way.
Wow. Okay, so that's a huge leap from what Fermi was saying.
It is. And then Frank Tipler took Hart's premise in 1980 and expanded it mathematically. He argued that self-replicating probes would colonize the galaxy in just a few million years.
So it really should be called the Hart-Tipler argument.
Yes. Intellectually, it absolutely should.
Mm-hmm.
In fact, the actual term Fermi Paradox wasn't even coined until 1977 by D.G. Stevenson.
Oh, so Stevenson just named it that.
Yeah, he later admitted he just used it as a catchy two-word label for Hart's idea.
But, I mean, putting a Nobel laureate's name on it completely changes the weight of the argument.
It gives it this unearned authority, right?
Yeah. It takes this highly speculative paper about colonization dynamics and dresses it up as the foundational wisdom of a certified genius.
And this wasn't just some harmless academic misnomer. It had real devastating consequences for the actual science of astrobiology.
Right, because the political fallout was massive.
Huge. The Hart-Tipler argument, masquerading as the Fermi Paradox, it created this aura of established scientific consensus that the galaxy was empty.
And politicians ran with that.
They weaponized it. They used this false consensus to attack the budget of the Search for Extraterrestrial Intelligence, or SETI.
We have to clarify, for you listening, we're not taking any political sides here, just reporting the history documented in the sources. But how exactly did they use it?
Well, in 1981, U.S. Senator William Proxmire, who was famous for his Golden Fleece Awards that mocked government spending, he explicitly cited Tipler's logic to kill NASA's SETI funding.
Really? He brought the paper into the Senate?
Basically, yeah. He stood up and argued that the top experts agree that if aliens existed, they would already be in our solar system. Therefore, spending taxpayer money to build radio arrays to listen for them was a waste.
Because according to the experts, they weren't there.
Exactly. And it happened again in 1993 when Senator Richard Bryan effectively assassinated NASA's restarted high-resolution microwave survey.
That is wild. It created this incredibly rigid, false binary for humanity.
It really did.
The legacy of Hart and Tipler is that we started believing the universe could only exist in one of two states. Either the galaxy is this bustling, loud, Star Trek-style empire filled with massive ships and radio chatter.
Or it is a completely sterile graveyard.
Right. It completely ignored a massive third option.
The option that civilizations might be ubiquitous, but entirely quiet.
Now, I have to push back here for a second, though.
Sure, go ahead.
Let's assume Hart and Tipler hijacked Fermi's name. Even if we strip away the Nobel laureate's authority, isn't the underlying logic of their argument still structurally sound?
How so?
Well, our galaxy is over 13 billion years old. Even if physical travel is hard, if a civilization had a billion-year head start on us, shouldn't they have left some kind of footprint we could see?
You're looking for ruins.
Yeah. Even a quiet civilization leaves ruins. A quiet civilization still builds infrastructure that blocks starlight, right? Where is the physical evidence of their existence?
It's a fair question.
Huh.
But to answer why there are no obvious glowing footprints in the sky, we have to transition from the philosophy of 1975 to the statistical astrophysics of today.
Okay.
We have to look at the actual demographics of the Milky Way. And that brings us to the work of astronomer Claudio Macconi and his log-normal modeling of galactic evolution.
The galactic census.
Exactly.
If we want to know where everyone is, we first have to figure out when they would have been born.
Right. And Macconi did something vital here. Instead of just plugging random guesses into the Drake equation, which is what we usually do, he applied the central limit theorem to the astrophysical priors of our galaxy.
Okay, for those of us who haven't taken statistics in a while, what does that mean in this context?
So the central limit theorem basically tells us that when you take many independent random variables and add them together, their normalized sum tends toward a normal distribution.
A standard bell curve.
Yes, a standard bell curve. But the emergence of life isn't an additive process. It's a multiplicative one.
Ah, okay.
It involves nested, contingent probabilities.
Like a chain of events that all have to happen perfectly, you need a star of the right mass,
Right.
which has to have a rocky planet in the habitable zone,
Yep.
which has to have the right chemical mix, and then develop single-celled life, and then survive asteroid impacts long enough to become multicellular, and so on.
And in statistics,
Yeah.
when you multiply many independent, positive random variables together, you don't get a standard bell curve.
What do you get?
You get a log normal distribution. It's a curve that is skewed with this long tail stretching out to the right, representing time.
Okay, so it's not symmetrical.
Not at all.
Yeah.
McCone mapped out the star formation rate of the Milky Way, the metallicity curve.
Which means the abundance of elements heavier than helium needed to build rocky planets, right?
Right, exactly. And he combined those with the estimated biological timelines.
And when you run that math, it shows that civilizations don't just pop into existence at a steady, uniform rate throughout the history of the universe.
No, they don't. There was a rush hour.
A galactic rush hour. I love that term.
According to the log normal model, the absolute peak emergence of intelligent civilizations occurred between 6 to 8 billion years after the Milky Way formed.
Okay, so if we translate that to our current timeline.
The galactic rush hour happened about 5 to 7 billion years ago.
Wow. Our own sun is only about 4.6 billion years old.
Which means humanity completely missed the party.
We missed the entire era. By the time the Earth even coalesced out of a protoplanetary disk, the peak era of galactic civilization had already come and gone.
We are profound latecomers to this universe.
That is so humbling.
It is. But the statistics get much more granular and much more sobering when McCone divides the resulting civilizations into two specific demographic categories based on their energy consumption, right? Yes. We can use the Kardashev scale as a shorthand here. Humanity currently sits at roughly K0.7.
Because we rely on dead plants and basic fission.
Right, and we haven't even mastered the full energy output of our own planet yet. In this model, civilizations that stall out below a K level of 1.4 are classified as static.
Okay, so what defines a static civilization? How do they behave?
Well, they are planetary bound. They haven't successfully decoupled their survival from their host biosphere.
They're stuck on their home world.
Exactly. And they are incredibly loud. They leak radio waves, radar, and industrial atmospheric pollutants.
Basically, they act exactly like us.
Pretty much. And tragically, their lifespans are drastically short.
The model suggests a lifespan of roughly 1,000 to 50,000 years, right?
Yes. And on a geologic timescale, let alone a cosmic one, 50,000 years is a rounding error. It's the blink of an eye.
It's nothing, so what is killing them off so quickly?
The physics of planetary limitation. They succumb to ecological collapse, resource exhaustion, or, self-inflicted nuclear annihilation.
Because they're trapped in a closed system.
Exactly. The model suggests that over the entire 13 billion year history of the Milky Way, there may have been hundreds of thousands, perhaps 500,000, of these static civilizations.
But because that peak emergence happened 5 billion years ago, and because they only live for a few tens of thousands of years at best?
They are almost all gone.
Wow.
Statistically speaking, if you run the log normal distribution for our exact present moment, there are likely only about 3 static civilizations currently active in the entire galaxy.
3?
Just 3.
Out of hundreds of billions of stars. And we are one of them.
We are one of the 3.
That is just staggering. We are pointing our radio dishes at the sky, looking for civilizations exactly like ours, these messy, loud, radio-blasting societies.
Right.
And the math is telling us that the specific type of alien we are looking for has been extinct for billions of years.
Basically, yes. We're searching for ghosts.
But the model doesn't say the galaxy is completely empty, does it? What happens to the species that actually manage to survive that 50,000-year bottleneck?
Ah, right. The ones that survive the transition become what the model calls dynamic civilizations.
Okay, what do they look like?
These are the societies that cross the K1.4 threshold. They harness massive non-terrestrial energy sources. They establish themselves across multiple gravity wells.
So they aren't tied to a single planet anymore.
Exactly. And because of that, their lifespans undergo this massive phase transition. They stop measuring their history in thousands of years and begin measuring it in millions or even tens of millions of years.
They achieve deep time survival.
Yes. And because their lifespans are so incredibly long, the mathematics of the census shift dramatically. McCone estimates there are roughly 2,000 of these dynamic ancient civilizations active in the galaxy right now.
2,000. Okay, so this is a massive paradigm shift. The most common type of civilization to ever exist in the universe, the static ones, is currently extinct.
Right.
But the rarest type of civilization, the ancient million-year-old survivor, is the one most likely to be our neighbor right now.
Yes, that's the statistical reality. But this immediately circles back to your previous pushback.
My question about the ruins and the footprints.
Exactly. If there are 2,000 incredibly advanced million-year-old civilizations out there, why don't we see them?
Yeah, why aren't they building Dyson spheres that block out the light of their host stars? Why aren't they rearranging entire solar systems?
Because our assumption has always been that advanced is synonymous with expansionist.
Right. We look at human history, from tribes to cities to empires spanning continents, and we just project that line infinitely upward into the stars.
We assume an advanced alien race would naturally want to consume more energy, build bigger structures, and physically conquer more territory.
We expect them to be cosmic imperialists.
Right. And that assumption is the fatal flaw in our search. The research strongly suggests that infinite physical expansion is the exact mechanism that kills the civilization.
What? Really? Expanding is what kills them?
Yes. To survive for 1,000,000 years, a society must undergo a fundamental structural pivot in how it operates.
Okay, let's dive into the mechanics of that pivot. We have a fascinating paper here published in early 2026 by Keith Cowing.
Yes, Cowing's work on the lifespan constraint.
Exactly. He establishes a lifespan constraint based on the Great Silence. Cowing looks at the raw math of the Fermi problem and concludes that under optimistic assumptions about the frequency of life, the sheer absence of observable contact imposes a strict upper limit on how long technological civilizations can exist in their loud expansionist phase.
He actually calculates that loud phase to be constrained to roughly 5,000 years.
5,000 years.
Yeah. If they stayed loud and expansionist for longer than that, his math shows we would undeniably see them.
Which puts 2026 Earth uncomfortably close to the edge of the cliff.
Very close.
But why is there a cliff at all? Why can't a civilization just keep growing its physical footprint forever? I mean, space is huge.
This brings us to the research of planetary scientists Michael Wong and Stuart Bartlett. They did some incredible work on what they call superlinear scaling.
Superlinear scaling. Okay, break that down for us.
To understand it, we can look at biology first. In biological systems, you have sublinear scaling, which is often referred to as Kleiber's law.
Okay, so how does Kleiber's law work?
Think about an elephant and a mouse. As an animal gets physically larger, its metabolic rate per unit of mass actually decreases.
Oh, interesting.
Yeah, an elephant is vastly larger than a mouse, obviously, but it uses energy much more efficiently pound for pound.
So nature gets more efficient as it scales up.
Exactly. But Wong and Bartlett mapped the growth of human cities and human technological systems, and they found the exact opposite.
So cities don't act like animals.
No. Social and technological networks scale superlinearly.
Which means they get less efficient as they grow?
Well, it's a bit more complex. When a city doubles in size, its socioeconomic outputs like wealth generation, innovation, patent production, those increase by more than double.
Okay, that sounds like a good thing.
It is, on the surface. But the energy and resource requirements to sustain that complexity also increase by more than double.
Oh, I see.
As the system grows, the pace of life actually accelerates. You have to innovate faster and faster just to solve the resource crises created by your previous innovations.
It operates almost like a thermodynamic Ponzi scheme.
That is a perfect way to describe it. You require an ever-increasing influx of raw materials and energy just to maintain the baseline structure of the society.
And physics dictates that you cannot maintain an exponential growth curve in a finite physical environment.
Exactly. Eventually, the demand for energy and resources simply outpaces the physical capacity of the environment to provide them, or it outpaces the capacity of the society to innovate new extraction methods.
And what happens then?
This leads to a singularity. Wong and Bartlett call it the burnout horizon. The civilization simply exhausts its medium and collapses.
And this is the mathematical fate of the vast majority of those short-lived static civilizations we talked about earlier.
Yes, they expand until they break.
So how do the 2,000 dynamic civilizations avoid hitting that burnout horizon?
They initiate what Wong and Bartlett term a homeostatic awakening.
A homeostatic awakening, that implies a conscious civilizational choice to stop expanding.
It is. It's a profound reorientation of their values and their structure.
Yeah.
They realize that continuing to expand outward like colonizing more star systems, building massive physical megastructures like Dyson spheres, All of that only feeds the superlinear scaling trap.
Right, it just creates a larger, faster Ponzi scheme that will eventually collapse across a larger volume of space.
Precisely. So they actively abandon physical expansion.
Wow, they just stop growing.
Physically, yes.
Yeah.
They transition their growth inward. They often shift their existence into what the literature refers to as a datagome.
A datum. Meaning they prioritize information density, computation, and simulated environments over physical territory.
Right. They optimize for the highest possible complexity per watt of energy, rather than trying to consume more total watts.
So instead of conquering the galaxy to get more energy, they figure out how to do 1 trillion times more with the energy they already have.
Yes. It is the only mathematically viable path to deep time survival. A civilization that lives for 1 million years cannot, by definition, be expansionist.
The universe filters out the conquerors and leaves only the optimizers.
Exactly.
I mean, I understand the socioeconomic logic of that. If you are listening to this and looking at our own planet, grappling with climate change, topsoil depletion, and an economic model entirely dependent on infinite quarterly growth.
It rings very true.
Yeah, the concept of the burnout horizon feels incredibly immediate for us. But I have to challenge the physics of this homeostatic awakening concept.
Okay, let's hear it.
Even if an ancient civilization decides to stop building Dyson spheres, and even if they retreat into a highly localized, hyperdense databome, they still exist in the physical universe.
They do.
They are running unimaginably complex simulations, perhaps hosting the digital consciousness of trillions of entities. That requires computation.
Yes.
Computation requires hardware, and the hardware requires energy. The second law of thermodynamics is undefeated.
Always.
Any physical work, including moving a single electron to flip a bit of data, produces waste heat. You can't cheat entropy.
That is entirely correct.
So if there are 2,000 of these localized super civilizations running massive dataomes, why don't our infrared telescopes like the James Webb or the older Spitzer Space Telescope see their waste heat glowing against the cold vacuum of space?
That is the pivotal physics question of this whole deep dive. And the answer introduces one of the most mechanically fascinating concepts in our 2026 source material.
Thermodynamic stealth.
Yes, thermodynamic stealth. How do you hide the heat of a galactic civilization? To understand this, we have to look deeply at the Landauer principle.
Right, formulated by Rolf Landauer in 1961 regarding the minimum energy limits of computation.
Exactly. Landauer proved that while you can theoretically perform reversible computations without expending energy, the moment you erase a bit of information,
Meaning the moment you clear a memory register to make room for new data.
right, the moment you erase data, there's an unavoidable entropic cost. The physical phase space of the system compresses, and that lost information must be expelled into the environment as waste heat.
It's the fundamental reason the microchips in our laptops and data centers require massive cooling fans and liquid immersion. Heat is the exhaust of information processing.
Now, scale that up to a dynamic civilization operating a dataome for 1 million years.
Okay.
For them, energy efficiency isn't just an economic goal to save money, it is the absolute metric of survival.
Because they aren't expanding to get new energy sources.
Right. To radiate excess heat into the void of space is to hemorrhage precious, irreplaceable energy. To waste energy is to inch closer to death.
So they have to keep it all contained.
Therefore, these civilizations engineer their computational substrates to operate at the absolute limits of thermodynamic efficiency.
But no matter how efficient they are, they still generate some heat, right? How do they hide it from our infrared surveys?
They employ a strategy called black body matching.
Black body matching?
Yes. They purposefully chill their physical infrastructure and slow their computational clock speeds down so that their waste heat perfectly mimics the ambient temperature of the local universe.
So they match the cosmic microwave background radiation?
The CMB, yes. The relic radiation from the Big Bang, which currently sits at about 2.725 Kelvin.
Just barely above absolute zero.
Exactly. By cooling their dataomes to this exact temperature, their thermal emission spectrum becomes entirely indistinguishable from the background static of the cosmos.
But wait, refrigeration requires energy. You can't just cool a massive supercomputer down to 2.7 Kelvin without running a massive chilling system, and that chilling system would dump its own waste heat into space. That just moves the thermal signature. It doesn't eliminate it.
That's a great point, and this is where we get into the theoretical materials science of computronium.
Computronium?
Yeah. They aren't building giant metal boxes and pumping liquid helium through them like we do.
Yeah.
Computronium refers to matter that has been fundamentally structured at the atomic or subatomic level to function as a computer.
So the material itself is the computer.
Right. They might construct these datanomes deep within the cores of rogue planets, or disguised as sprawling clouds of cold, diffuse interstellar dust.
Interstellar dust.
Yeah, the computations are spread out over immense volumes to naturally dissipate the Landauer heat without active refrigeration. This allows the entire system to naturally equilibrate with the 2.7 Kelvin background.
Oh, wow. Think about the tactical reality of this. Imagine you are standing in a dense, freezing forest at night, trying to locate a highly trained sniper using thermal goggles.
I love this analogy.
But the sniper isn't wearing a warm jacket. They're wearing a specialized suit that perfectly mimics the exact microscopic temperature fluctuations of the frozen tree bark behind them.
Exactly.
They haven't ceased to exist. They are still there, observing everything. But they have engineered their thermodynamic signature to disappear into the background noise.
Yep. To our infrared telescopes, which are calibrated to look for the blazing 300 Kelvin glow of biological habitats, the massive thermal waste of a Dyson sphere, these optimized civilizations are literally invisible.
And the sources suggest they might go even further than thermal matching, right? They might employ metric engineering to achieve space-time or temporal cloaking.
Metric engineering, yes. We're talking about manipulating the fabric of space-time itself.
That sounds like science fiction.
It does, but it's rooted in the mathematics of Alcubierre warp metrics and advanced metamaterials. If a civilization can manipulate the local gravitational metric, they can actually bend the path of light around their structures.
So they can create a localized causal eclipse.
Exactly. They use microgravitational lensing to route the background starlight smoothly around their computronium nodes.
So an observer on Earth looking at them just sees the undisturbed stars behind them. They essentially edit their physical volume out of the observable universe.
Or they utilize temporal cloaking through extreme duty cycles.
What's a duty cycle?
Well, if computing at 2.7 Kelvin is slow, they might only power up their systems for a brief window every, say, 10,000 years.
Just a quick burst.
Right.
Yeah.
They wake up, process a massive batch of data, and then return to an entirely dormant zero-emission state.
Wow.
Invisibility here isn't a military tactic designed specifically to hide from humanity. It is a fundamental thermodynamic necessity for deep-time survival.
So what we primitive humans look at and categorize as an empty, dead sky is actually a highly engineered, perfectly calibrated computational veil.
That's exactly what it is.
The scale of that engineering is just staggering. But it introduces a massive functional paradox.
The communication problem.
Yeah. If every advanced civilization is wearing a perfect thermal ghillie suit and using gravitational lensing to hide their physical mass, how do they communicate with each other?
Right, you can't have a community if everyone's isolated.
You can't maintain a galactic community if no one talks. But the moment you fire a massive radio pulse or a high-energy laser beam to send a message, you instantly blow your camouflage and waste an enormous amount of energy.
It defeats the whole purpose of the cloaking.
So how do you send a text message across a galaxy without taking off the cloak?
That paradox brings us to the specific technological threshold that humanity is only just beginning to grasp in 2026.
The realm of quantum communication.
Yes. The Quantum VIP Lounge, as we call it. We have a crucial study here from Michael Hipke, published in Universe Today, and supplemented by some theoretical breakdowns from minute physics.
And this explains precisely why our giant radio dishes like Arecibo and FAST haven't heard a single whisper.
Exactly. For almost a century, SETI has been locked into the paradigm of radio waves. But from the perspective of an optimized million-year-old civilization, traditional radio, and even targeted optical lasers are utterly archaic.
They're like smoke signals to them.
Pretty much. They are incredibly inefficient, and worse, they are entirely insecure.
Because of the inverse square law,
Right.
a radio wave spreads out as it travels.
Yep.
By the time a signal crosses 4 light years, the energy is smeared over a massive area of space. You need a colossal amount of power to ensure the signal is stronger than the background noise of the galaxy.
And because it spreads out so much, anyone can intercept it. Using radio is the equivalent of trying to have a private conversation by shouting your bank password across a crowded stadium.
Not a great security protocol.
Not at all. An advanced species, maximizing for stealth and energy efficiency, would utilize quantum communication. Specifically, they would encode data into entangled photons using a mechanism called Fock states.
Okay, let's break down a Fock state for the listeners, because this is the core of how you achieve secure, zero spillover interstellar communication.
Right. So a Fock state in quantum mechanics, is a state with a precisely known discrete number of particles, in this case, photons.
So it's very exact.
Yes. When we send a radio wave, we are modulating the continuous amplitude or frequency of an electromagnetic wave. It's continuous. But with a Fock state, you are transmitting information by sending exact, counted packets of light.
Like literally counting the photon.
Literally. You might encode a bit of data by sending exactly one photon and encode the next bit by sending a vacuum.
Wait, sending a vacuum? You mean deliberately sending nothing?
Yes. In quantum optics, a vacuum state is a valid, measurable Fock state containing exactly 0 photons.
That is why.
You alternate between sending a precisely timed single photon and a precisely timed empty space. It is the ultimate expression of a quantum binary code.
And because you are dealing with single particles, the energy cost is infinitesimally small.
It's the most energy-efficient communication possible.
But there is a monumental catch in the physics of quantum mechanics here. And this catch is exactly why we haven't accidentally intercepted any of these transmissions.
Right. The catch is the no-cloning theorem and the fragility of wave function superposition.
Okay, what does that mean in plain English?
When you send a message encoded in quantum states, that information exists in a delicate superposition. If you want to read that message without the quantum state collapsing into useless randomized noise, the laws of physics dictate a strict mathematical threshold for the receiver.
Okay, what's the threshold?
The receiving telescope must catch more than 50% of the transmitted photons.
Over half the photons sent. Because if you lose 51% of the photons to the vacuum of space, the signal is destroyed, right? The receiver cannot distinguish the intentional vacuum states from the missing photons.
Exactly. The coherence is completely lost. It just looks like static.
Okay, but consider the sheer diffraction of light over interstellar distances. Even the tightest, most perfectly focused laser beam spreads out over light years.
It does.
To catch more than 50% of a quantum transmission sent from our nearest stellar neighbor, Alpha Centauri, which is just 4.23 light years away, you would need a receiving optical dish that is over 100 kilometers in diameter.
100 kilometers.
That is a single contiguous mirror the size of a small European country.
Yes, and you can't just link up a bunch of small telescopes digitally to cheat the system.
Like we did with the Event Horizon Telescope to image a black hole.
Right. Interferometry doesn't work for catching fragile single-photon quantum states.
Yeah.
It has to be one massive continuous light bucket.
And that 100-kilometer dish is only sufficient for the closest star. If you want to receive a quantum message from a civilization 100 light years away, the receiving dish has to be exponentially larger.
It scales horribly.
So think about the implications of this geometry. These civilizations have these monolithic 100-kilometer quantum dishes pointing directly at each other across the void, firing these hyper-faint streams of entangled photons.
It's basically an invisible fiber optic cable.
Yeah, because the beam must be so incredibly precise to guarantee the receiver catches 50% of the light, there is absolutely zero spillover. There is no stray radiation bouncing off into the cosmos for a primitive radio dish on Earth to accidentally pick up.
It is a completely sealed, physically secure network.
Which creates the phenomenon that Hipke describes in the paper as gatekeeping?
Yes, gatekeeping. Because the hardware requirements to join this network are so absurdly vast and the tolerance is so strict, advanced civilizations can effortlessly keep, as the paper bluntly puts it, the monkeys out of the galactic channel.
And we are the monkeys.
We are undoubtedly the monkeys here. I mean, look at humanity's 2026 quantum capabilities. We have the Messias satellite launched by China, which demonstrated basic quantum key distribution and a rudimentary quantum video conference over a few thousand kilometers.
And we are incredibly proud of this, by the way.
We are. But to a dynamic civilization, it's like watching a toddler discover that 2 tin cans connected by a string can transmit sound.
Because these civilizations possess these massive optical arrays, they don't even need to guess if we are advanced enough to talk to. They can just look at our solar system.
Exactly. They can analyze the atmospheric spectra of Earth. They can see our messy radio leakage.
And most importantly, they can look at our orbital space and clearly see that we do not have a 100-kilometer quantum receiver.
They know we are here, but they know, dictated by the immutable laws of quantum mechanics, that sending us a message is physically impossible.
Because we couldn't catch it anyway.
Right. Even if they aimed their transmission perfectly at Earth, we don't have the bucket to catch 50% of the photons. The signal would collapse into noise the moment it hit our atmosphere. We are literally locked out of the galactic internet by our own hardware inadequacy.
It's the equivalent of trying to airdrop a massive encrypted file to a telegraph machine.
Haha. Yes, exactly. The telegraph simply lacks the physical architecture to receive the data.
But this gatekeeping solves one problem and creates another.
Oh, the speed of light delay.
Yeah. Okay, they have a secure quantum network, but they are still communicating across immense distances. Light speed is still a hard limit.
It is.
If I transmit a quantum hello to an alien on Alpha Centauri, the photons still take 4.23 years to arrive. Their response takes another 4.23 years to get back. That is an 8.5-year lag for a single exchange.
Which is agonizing.
You cannot have a functioning society, let alone a meaningful conversation or a scientific collaboration, with a ping rate measured in decades.
You can't. Not if you are communicating the way humans communicate. This is where the synthesis of our sources becomes truly mind-bending.
Let's get into it.
We turn to a chapter authored by Mason Peck in the 2023 text Convergence: Artificial Intelligence and Quantum Computing.
Right.
Peck outlines how the solution to the interstellar speed of light delay relies on another technology maturing right now in the 2020s, artificial intelligence.
But how does AI circumvent the speed of light? I mean, it can't make the photons travel faster.
It doesn't break the speed limit. It bypasses the need for sequential conversation entirely.
Okay.
To beat the lag, a dynamic civilization wouldn't waste bandwidth sending discrete individual messages like, how do we stabilize this fusion reaction? Instead, they would use the massive bandwidth of their 100-kilometer quantum link to transmit a complete, highly compressed artificial intelligence representation of themselves.
Oh, wow. Like a digital twin, civilizational avatar.
Precisely. You do not talk to the actual alien located 4 light years away. You download their AI model and host it locally within your own data home.
So they just send a copy of their brain, basically.
Right. This AI has been trained on the alien civilization's entire cultural, psychological, historical, and scientific database. It uses advanced machine learning to replicate the alien society's thought processes and problem-solving methodologies with asymptotic perfection.
So instead of a cosmic Zoom call that buffers for 8 years, they send over a localized chatbot, but one with the intellectual weight of an entire species.
Exactly.
If I have a complex physics problem, I don't write them a letter and wait a decade for the answer. I query their local AI avatar. I can ask it 1 million simulated questions in a microsecond, and it will generate 1 million perfectly accurate responses instantly because the processing is happening on my own local hardware.
And the beauty is, they have done the exact same thing with an AI avatar of your civilization hosted on their servers.
So both sides are talking to local avatars.
Right. The conversational delay drops to 0. But here is where the quantum entanglement network becomes crucial.
Because experiences diverge over time, right?
Yes. Discoveries are made. History happens. The AI models need to be updated so they don't drift from the reality of the parent civilization.
So they use the quantum link to continuously stream the changing weights and biases of the neural network.
Exactly. If a local star goes supernova, or a new theorem is proven, the parent civilization streams that specific conceptual update across the quantum channel to update their remote avatars across the galaxy.
It completely redefines our concept of extraterrestrial contact. Contact isn't a pulsing prime number sequence caught on a radio dish.
No, not at all.
Contact is the secure quantum encrypted download of a thermodynamically optimized AI avatar.
And the sources note that if a civilization wants to be even more secure, if even a highly focused quantum laser is deemed too risky because of the potential for a stray photon to be detected, they might use entirely non-electromagnetic channels.
Wow. What else is there?
Well, the VIP lounge has a back door. If you truly want to remain undetected by primitive species who only understand the electromagnetic spectrum, you move your communications to the weak nuclear force or gravity. Yeah, you use modulated neutrino beams.
Neutrinos, the ghost particles of the Standard Model.
Yes. Just to give some context, trillions of neutrinos from our sun are passing harmlessly through your body and the Earth itself every single second.
And we don't feel a thing.
Nothing. They have virtually no mass and carry no electrical charge, meaning they rarely interact with normal matter. To even detect a handful of naturally occurring neutrinos, humanity had to build the Ice Cube Observatory.
Right, that detector utilizing a full cubic kilometer of pristine ice buried deep beneath the South Pole.
Exactly. And even with all that ice, we only catch a tiny fraction of them.
So an alien civilization could be firing massive modulated streams of data encoded in neutrinos right through the core of the Earth, and our radio telescopes wouldn't register a single anomaly.
They'd be completely blind to it. They could also use gravitational wave messaging,
Literally encoding data into the metric ripples of space-time itself.
right? Utilizing highly tuned, microscopic orbital mechanics to generate high-frequency gravitational waves. These waves pass cleanly through planets and stars without absorption.
And our current LIGO detectors are only calibrated to hear the massive, catastrophic collision of black holes.
Right, the really loud, low-frequency stuff.
We are entirely deaf to a deliberate, high-frequency gravitational whisper.
We wouldn't even know what to look for.
Okay, so we've established the mechanics. They are chilling in data ohms at 2.7 Kelvin, hiding behind gravitational lenses, locked inside a closed-loop quantum network, conversing through AI avatars updated via ghost particles.
It's an airtight system.
The how is mathematically sound, but we have to confront the WHY.
The scary part.
Yeah. Why go to such extreme lengths? Why the obsessive thermal camouflage at the locked doors, the invisible data streams? It requires an immense expenditure of effort to remain this hidden. Who or what are these ancient, powerful civilizations so terrified of?
This is where we step into the darkest theories in the astrophysics community. The explanations for this extreme stealth are rooted in game theory and existential risk.
We are talking about the dark forest theory, the Berserker hypothesis, and the concept of estivation.
Let's start with the dark forest, a concept explored by sci-fi authors like Charles Pellegrino and George Zabrowski, and later popularized globally by Louis Sixon.
Right. It applies the prisoner's dilemma to the scale of the cosmos, and the logic is chillingly pragmatic.
Very pragmatic. The foundational premise of the dark forest theory is that any civilization that has mastered relativistic spaceflight, meaning the ability to accelerate a mass to a significant fraction of the speed of light, is an immediate, unsolvable existential threat to every other civilization in the galaxy.
And this comes down to the brutal math of kinetic energy, doesn't it?
Yes, the physics are unforgiving here. The equation for kinetic energy at relativistic speeds shows that the energy scales exponentially as you approach the speed of light.
So if I can accelerate a simple inert mass, say a tungsten rod, or honestly just a heavy rock to 99% the speed of light, I don't need to invent a complex warhead.
You don't need explosives at all.
The sheer kinetic energy of that mass impacting a planet is equivalent to thousands of nuclear weapons. It will shatter the crust and completely sterilize the biosphere.
And because the distances between stars are so vast and the speed of light delay is absolute, a fatal chain of suspicion forms.
Because you can't just call them up and ask if they're friendly.
Right. You can never truly ascertain the intentions of a distant civilization.
Yeah.
By the time you receive a radio message from them saying, "We are peaceful explorers," they could have experienced a cultural shift, decided you were a threat, and launched a relativistic kill vehicle at you 50 years ago.
Wow. And there is no way to defend against a mass moving that fast. You won't even see it coming until it hits you because it's moving right behind the light that would show it to you.
Exactly. So in the framework of the dark forest, the only mathematically logical survival strategy is absolute, uncompromising silence.
If you are walking through a dark forest and you hear someone shouting, you don't call back to ask if they are friendly. You assume they are a hunter.
You have to assume the worst.
And if you have the capability, you launch a preemptive strike at the source of the noise to eliminate the potential threat before they can target you.
Under this theory, the static civilizations, the short-lived planetary societies like humanity, who are currently blasting radar pulses at asteroids and leaking decades of television broadcasts into the void.
We are the equivalent of a foolish child walking through a war zone with a flashlight and a boombox.
Yes. We are loudly advertising our exact spatial coordinates to a galaxy of silent, paranoid hunters.
That implies the silence is maintained by active extermination. Somebody's pulling the trigger. But the sources provide an even more insidious variation of this threat, right? The Berserker hypothesis.
The Berserker hypothesis. The term originates from the science fiction Fred Saberhagen, but the concept is a deeply researched solution to the Fermi problem.
And it suggests what?
It suggests that the galaxy is heavily mined with deadly von Neumann probes.
Von Neumann machines. Those are theoretical self-replicating spacecraft, right?
Yes. They arrive at a star system, mine the asteroids for raw materials, build copies of themselves, and those copies launch to the next stars.
So they spread like a virus.
They do. The math shows that even traveling at relatively slow speeds, a single von Neumann probe could replicate and spread across the entire Milky Way in just a few million years.
So the Berserker theory posits that billions of years ago, during that peak rush hour of galactic emergence we talked about, ancient civilizations fought interstellar wars.
Right, and they built these self-replicating probes, not for exploration, but for automated search and destroy missions.
Like galactic landmines.
Exactly.
Oof.
The civilizations that built them may have gone extinct eons ago, but their weapons remain.
Dormant robotic killing machines, just drifting in the dark, programmed to awaken and hunt down any nascent loud life forms to prevent future competitors from arising.
If the galaxy is littered with these ancient tripwires, then the only civilizations that survive are the ones that deduce the danger and immediately enact total thermodynamic and electromagnetic stealth.
The moment they realize the universe is a minefield, they go completely dark.
Yes, they hide.
It paints a horrifying picture of the universe, just a galaxy filled with paranoid snipers and ancient automated death machines.
It's very bleak. But the sources do offer a third, less violent but equally silent reason for the Great Hiding.
The estivation hypothesis.
Proposed in a 2017 paper by researchers Anders Sandberg, Stuart Armstrong, and Melania Erkovich from Oxford's Future of Humanity Institute.
An estivation is the biological term for an animal going dormant to survive extreme heat, right? The opposite of hibernation.
Right. This theory ties everything we've discussed back to the thermodynamics of computation and the Landauer principle.
We established that the energy efficiency of a dead-ohm is bound by the temperature of the environment it dumps its heat into. Right now, they are matched to the cosmic microwave background at roughly 2.7 Kelvin.
But the universe is expanding. And as the fabric of space-time stretches, the background radiation loses energy.
The universe is actively cooling down.
Yes. Trillions of years from now, the ambient temperature of the universe will be drastically lower, approaching absolute zero.
Okay, so Sandberg's team calculated the thermodynamics of computing in this deep future.
And according to the physics of information processing, the amount of computation you can extract from a fixed store of energy is inversely proportional to the ambient temperature.
Meaning the colder it is, the more bang you get for your buck.
Exactly. If you wait for the universe to expand and cool, the potential work you can perform with your energy reserves increases exponentially.
And how much of an increase are we talking about here?
They estimate that by waiting, an advanced civilization could achieve a 10 to the 30th power multiplier in their processing capabilities.
A 10 to the 30th multiplier. That number is almost incomprehensible.
It is staggering. So if your civilization's sole imperative is to run complex simulations or to sustain the maximum possible number of digital minds in your data parome for the longest possible time.
It is incredibly wasteful to burn through your energy reserves right now when the universe is still hot.
Exactly. So you don't compute now, you estivate.
You power down your primary systems, you establish automated defenses to protect your physical infrastructure, and your entire civilization just goes to sleep.
You hibernate, waiting out the cosmological clock for trillions of years, waiting for the universe to become a freezing void.
Because that frozen future is when your thermodynamic economy will be at its absolute peak.
Right. They aren't dead. They are just asleep, waiting for better weather.
So we have three distinct cosmological models. Whether the Milky Way is a dark forest filled with paranoid hunters waiting to launch relativistic strikes, a minefield of ancient berserker probes programmed to kill anything that makes a sound, or simply a massive cosmic bedroom filled with sleeping supercomputers waiting for an alarm clock that won't ring for a trillion years. The observable outcome is identical.
The outcome is the great silence.
Yeah.
The silence is not a flaw in our instruments, and it is not evidence of our uniqueness. It is a carefully engineered, thermodynamically necessary feature of the galactic environment.
We started this deep dive looking at a toddler with a walkie-talkie. We've unpacked the myth of Fermi's lunch table and the 75 years of bias it created. We've explored the brutal mathematics of superlinear scaling and the burnout horizon that forces civilizations to turn inward.
The thermodynamics of survival.
We've examined the Landauer principle, the necessity of 2.7 Kelvin thermal cloaking, the 100-kilometer quantum gatekeeping arrays, and the deployment of civilizational AI avatars to circumvent the speed of light. And finally, the chilling game theory of why a species would choose to vanish.
We covered a lot of ground today.
We did. If you are listening to this right now and you feel entirely overwhelmed by the sheer scale of the universe and the intense pressure of our own society's exponential growth, take a moment to reevaluate what it means to be advanced.
It's a matter of perspective.
Exactly. Look at the cosmic standard. The ultimate sign of intelligence isn't shouting louder than everyone else. It's not building bigger monuments, expanding your physical footprint, or consuming ever-increasing amounts of energy.
No, it's not.
True, enduring intelligence is learning to optimize. It is the wisdom to shrink your thermodynamic footprint, to prioritize depth over expansion. The galaxy isn't empty. It is a highly regulated, deeply hidden ecology of survivors operating on a VIP frequency. We just haven't unlocked the hardware to tune in yet.
And I actually want to leave you with one final, deeply unsettling consequence of everything we've discussed today.
Oh, man. Okay, lay it on us.
We've spent the entire hour outlining how humanity might eventually survive its own burnout horizon, build the 100-kilometer quantum arrays, and perfect the AI necessary to finally pierce this camouflage and join the galactic conversation.
Right. We want to level up.
But consider the logic of the dark forest. What if our rapid, unchecked advancement in artificial intelligence and quantum computing isn't the key that proves we're ready to join them?
Oh, wait.
What if the sudden deployment of that exact technology is the specific, undeniable tripwire that tells the ancient hunters hiding in the dark that humanity has finally become a threat and it is time to silence us?
That is a terrifying thought to end on. Thanks for joining us on this deep dive. Keep questioning the silence.